Hello and welcome, everyone. Today, we are excited to present our work on the topic, Scene Captioning using Deep Learning and Computer Vision Techniques. This project is part of our coursework for Computer Vision. I am your presenter today. Our group consists of 3 members, Moturu Himesh, Besta Bhavya Sree, and Akshay Reddy Velugati. In this presentation, we will take you through our journey of building an intelligent system that connects the visual world with the world of language. We will explore how we moved beyond simple object detection to create a model that truly understands the context of a scene and can describe it in natural, human-like language. We will cover our problem definition, the dataset we utilized, our proposed architecture using state-of-the-art transformers, and the results we have achieved. Let's begin with an introduction to the domain. Scene captioning is one of the most fascinating and challenging tasks in modern artificial intelligence because it sits right at the intersection of 2 major fields, computer vision and natural language processing. While computer vision gives machines the ability to see pixels and identify patterns, natural language processing gives them the ability to speak and understand grammar. Scene captioning bridges these 2 worlds. The core goal of our project is to develop a system that can input a static image and output a descriptive, grammatically correct sentence. This is not just about identifying a dog or a frisbee in a picture. It is about understanding the relationship between them, recognizing that the dog is catching the frisbee in a park. This technology has immense practical value. It is the backbone of accessibility tools for the visually impaired, allowing screen readers to describe photos on the internet. It is also crucial for automated content indexing, enabling search engines to find images. So, what is the specific problem we are solving? To understand this, we must look at the limitations of traditional computer vision systems. Standard image classification models are excellent at label prediction. If you show them a busy street, they might output a list of tags: car, person, traffic light. However, a list of tags is not a description. It lacks context, action, and flow. The problem is that traditional convolutional neural networks, or CNNs, struggle to capture the global context and the sequential nature of language simultaneously. Earlier attempts to solve this used CNNs for images and recurrent neural networks, like LSTMs, for text. While these were a step forward, they often failed to capture long-range dependencies, leading to captions that were repetitive or grammatically broken. Our objective in this project is to bridge this gap. We aim to implement a system that generates meaningful, contextually accurate natural language descriptions. To do this, we are moving away from older architectures and adopting modern, attention-based approaches that can process the entire image context at once. Data is the foundation of any deep learning project. For this task, we selected the Flickr 8K dataset. As the name implies, this dataset consists of 8,000 images collected from Flickr, covering a wide variety of real-world scenarios, from people and animals to sports and landscapes. However, the image count is not the most important feature. The critical aspect of Flickr 8K is its rich annotation. Every single image in this dataset is paired with 5 different captions written by actual humans. This totals 40,000 captions. This diversity is essential for training. For example, one human might describe an image as a dog running, while another might write a black puppy chasing a ball. By training on these variations, our model learns that there are multiple correct ways to describe a scene. In our pre-processing pipeline, we parse these text files to map images to their captions. We also performed extensive text cleaning, removing punctuation, normalizing text to lowercase, and tokenizing the sentences to ensure the data was ready for our language model.
Now, let's dive into the technical core of our project, our proposed approach. We have chosen to implement the BIP2 architecture, which stands for Bootstrapped Language Image Pre-training. This is a state-of-the-art architecture that significantly outperforms older CNN LSTM models. Our pipeline consists of 3 main stages. First, we use a visual encoder. Instead of a standard CNN, we are using a vision transformer or VIT. This splits the image into patches and processes them using self-attention, allowing the model to capture global features effectively. Second, we have a component called the QFormer or Querying Transformer. This acts as a bridge. It takes the heavy, high-dimensional visual embeddings from the VIT and compresses them into a set of query vectors that are compatible with a language model. Finally, the third stage is the text decoder. We utilize Flan-T5, a powerful large language model. This decoder takes the visual cues from the QFormer and generates the final caption token by token, ensuring the output is not just accurate, but also fluent and grammatically robust. Implementing such a complex architecture requires a robust software stack. We built our solution primarily using Python, leveraging the PyTorch framework for deep learning operations. For the model components, we utilized the Hugging Face Transformers library. This was a strategic decision. Training a vision transformer and an LLM from scratch requires massive computational power, far more than what is available on standard machines.
Thank you for your time and attention.
By using Hugging Face, we were able to load pre-trained weights for the VIT and Flan-T5 components. This transfer learning approach allows us to fine-tune the model for our specific dataset without starting from zero. Our implementation pipeline involves several steps: loading the image using the PIL library, preprocessing it with OpenCV to resize and normalize pixel values, and then passing it through our model to generate text tokens. We also used pandas and NumPy extensively for handling the large annotation files and managing the dataset splits. Let's look at the qualitative results we have achieved in Phase 1. These examples demonstrate the model's ability to understand distinct scenes. In the first sample, we fed the model an image of a man wearing a hat. The generated caption was, "A man in an orange hat staring at something." This is a highly accurate result. The model didn't just see a person, it correctly identified the specific attribute, the orange hat, and the action of staring. In the second sample, we used an image of a child on a playground structure. The model output: a child playing on a rope net. Again, this highlights the strength of the vision transformer. A traditional model might have been confused by the complex texture of the net, but our attention-based model successfully resolved the visual features to identify it as a rope net. These qualitative results confirm that our pipeline is working correctly and the QFormer is successfully transmitting visual concepts to the language model.
While visual inspection is promising, we need scientific metrics to quantify our model's performance. We are evaluating our system using 3 standard industry metrics: BLEU, Rouge, and Meteor. The BLEU score, or Bilingual Evaluation Understudy, measures the overlap of n-grams between our generated caption and the 5 human reference captions. It essentially checks for precision how many words in our output were correct. Rouge, on the other hand, focuses on recall. It measures how much of the reference content our model managed to capture. Finally, Meteor is used to assess fluency, as it accounts for synonyms and stemming, giving us a better idea of semantic accuracy. No engineering project is without its challenges. Throughout our project, we made several critical observations. First, while the model excels at clear, distinct scenes like a dog on the grass or a person jumping, it struggles with highly cluttered or abstract images. In complex scenes with dozens of objects, the model sometimes defaults to generic captions, such as a group of people standing together, rather than describing the specific interactions. Another challenge we faced was the computational cost. Transformer-based models are memory-intensive. The self-attention mechanism in the vision transformer requires significantly more RAM than traditional CNNs. This posed a constraint on our batch sizes during inference. We also observed that fine-tuning the hyperparameters is crucial. Slight changes in the decoding strategy, such as beam search width, had a massive impact on the creativity and accuracy of the resulting captions. To conclude, we have successfully designed and implemented a scene captioning system using the Flickr 8K dataset and the BLIP2 architecture. We have demonstrated that by combining the visual feature extraction capabilities of vision transformers with the generative power of large language models, we can create systems that truly understand visual scenes. This project highlights the shift in computer vision from simple classification to complex multimodal understanding. Moving forward, our next steps include finalizing the quantitative metrics and exploring the addition of a text-to-speech module to read the captions aloud, which would complete the loop for a fully accessible assistant. Thank you for your time and attention.